Now let us go to the other one, that is the rupture disk. Okay, let us first understand what a rupture disk is. A rupture disk or a bursting disk is a non-reclosing pressure relief device. Reclosing means it again closes, so it opens and closes. Pressure safety valve works in that fashion. So whenever it is required, it opens, and whenever its job is done, it closes. But in this case, it ruptures, it bursts. Okay, so it is sort of one-time use device. So it is a non-reclosing pressure relief device, which is used in process safety instrumentation to protect equipment from overpressure or vacuum condition. It is designed to burst at a predetermined pressure, allowing excess pressure to be safely released. So the job of pressure safety valve and the rupture disk, they are same. And in addition to the overpressure, the rupture disk also caters to the vacuum condition, which pressure safety valve doesn't do, but rupture disk does. There are certain common applications. Obviously, the household application I have already discussed how it is done in a pressure cooker, but industrially, this is a common backup protection for a PSV. Even in the case of pressure cooker, this rupture disk is a backup protection or the extra layer of protection. Okay. It can be a standalone overprotection also. I mean, there might be a case where there is no pressure safety valve and there is only a rupture disk. For instance, a reactor or storage tank or piping system, or more commonly in vacuum tank. There we probably cannot use the pressure safety valve, so we have to use rupture disk. That's what it is written over here, vacuum protection. It prevents the vessel collapse under vacuum condition, and the emergency pressure relief, where the fast relief is crucial, like steam boilers, chemical reactors. These are the characteristics of rupture disk. It is non-reclosing. Just now we have discussed what it is. It should have fast response. Obviously, pressure safety valve also should be of fast nature, but rupture disk is faster. And its reliability should be very high because it is the backup for pressure safety valve. So even if there is a pressure safety valve and in an unfortunate event it fails, then the rupture disk should remain reliable enough to burst and maintain the safety of the whole process. So rupture disk should not fail at all. So there should be high reliability on that. And it has a leak-tight seal, so it ensures zero emission under normal operating condition. The set pressure should be customizable. It can be 10%, 20% of operating condition or whatever it may be. There are various options for material selection like stainless steel, graphite, nickel, Teflon, depending upon the process. And no maintenance is required because it doesn't have any moving part. So the mechanical failure chance is reduced quite a lot. Okay. So it is a fit and forget kind of thing. Obviously, it is cost effective because initial cost is low, so it is cost effective. Then there are various types of rupture disk. They may be forward acting, reverse acting, graphite rupture disk, composite rupture disk. Okay, each and every type has their own characteristics and they are usable for particular situation. They are listed over here. Here we find a comparison between rupture disk and PSV. The rupture disk is not reclosing, but PSV is reclosing. Response time is better in case of rupture disk. There is zero leakage guarantee for rupture disk, but it is not so for PSV. Rupture disk has precise set point for overpressure handling, whereas PSV can tolerate some minor overpressure. Cost-wise, rupture disk is cheaper than PSV, and maintenance, rupture disk minimal, PSV has to have regular maintenance check. Now, let us take a rupture disk and connect to the other pressurized flow, that is NGL prod. This is a liquid flow. Okay, so let us connect over here just like before. Yeah, so this rupture disk is getting connected with NGL. So let us open this. Just like before, we have got the set of operating temperature and operating pressure, design temperature, design pressure. Now we have to set the design temperature and pressure. So let us take it as a reference value only. Okay, in this example, let us take reference value. Although it is not justifiable, we have to take slightly higher than the operating case, but let us take this one and see how it goes. Then we have to choose a scenario. First, we have to create a scenario. And this scenario, let us open it. So this scenario type, let us take a fire situation. Okay, because it is a liquid flow. So there might be a possibility of leakage somewhere and the fire emergency may always appear. So let us take a fire scenario. The stream, we select the NGL prod. Okay, so this is the stream we have selected. Then let us not choose L by D method. Let us go back to the homogeneous equilibrium method, which we have already worked with. Now here you see relieving pressure is 82.20. But that shouldn't happen, right? Because we have taken the set pressure to be, what is our set pressure? Set pressure is same as the operating pressure, that is 67.93. And the back pressure is 10%, that is 6.793. But the relieving pressure should be 67.93 plus 6.793. So it should be 74.72, right? So this should be the relieving pressure. But what pressure we are getting? We are getting 82.20. Why? Because remember, we learned over here, the back pressure is usually 10%, but it is 21% for fire emergency. We have taken their fire emergency, right? So it is 67.93 multiplied by 1.21, 21%. That is 82.1953. Okay, that's exactly we are getting over here. Okay, so remember, it is a fire situation. Okay, Anyway, let us take the relieving flow not as calculated. We take the reference one, and the reference one is 2895 kg per hour. Okay, it is 28952 kg per hour. So 28,952. So it is 22.895 into 10 to the 4 kg per hour. That is the required relieving flow. And relieving temperature we have to provide. So let us take the reference temperature only. Yes. And orifice calculation complete, but we have to do the sizing. So let us take 1.90. Okay. Go to fluid properties. Relief composition. In the relief composition, you will find almost nothing for methane, ethane, propane. But butane onwards, you will find some component over there. Especially butane, you will find PC200, PC300. These three are quite high. Now go to PRD data. So in the PRD data, it is rupture disk. It is not relief valve, right? It is rupture disk only. So it shows like this. PSV, you remember? PSV, it was like this. This is the relief valve, PSV. Whereas RD, rupture disk, it looks like this. Okay. And the discharge too, we can use the high pressure flare. And these are the rupture disk type: reverse acting, forward acting, graphite. We just saw that, right? Forward acting, reverse acting, graphite, composite. So based on the type of rupture disk required for your case, you can choose from here. The disk material you can choose from aluminium, nickel, whatever. Stainless steel is also there. Then go to rating. Here you can see the overpressure. Allowable overpressure is 21%. So 67.93 multiplied by 1.21 will give you 82.2. Now the selected RD diameter 1.90, you are using 44.22% of the orifice area. So that is the reason you are getting the green stripe. If you use a smaller one, then it is above 95%. So it is not correct. And if you take higher one, then it is taking less than 30%. So it is not correct. So this one we chose. Let us keep it at there. Finally, line sizing. Line sizing, it is very high flow, rated flow. Rated flow is very high. So we will do it for required flow, which is this one. We will choose the schedule 40. This also 40. ND will take say 2. This one also will take 2. Okay. Here you see we have to click the run sizing, but here according to section API, the inlet pipe to rupture disk using discharge coefficient must be less than 8 times of pipe diameter in length. Okay. Now inlet pipeline we have taken 50 meter, but 8 pipe diameter is 0.41 meter. So this needs to be less than 0.41 meter. Similarly, outline pipe, it must be less than 5 pipe diameters in length. Discharge pipe length we have given at 50, but it should be less than 0.25. So let us take this one 0.4 and this one 0.24 and try. So let us take 0.4 and this one 0.24. Okay, so those two things are gone. Only click line sizing. Let us check the line sizing. Yeah, the pressure drop check is okay. So we are done with the rupture disc. Now the last one is storage tank protection. Now the low pressure storage tanks are used in the process plant under specific conditions where handling volatile, inflammable or sensitive liquids require controlled containment at low pressure. So these tanks function as safety devices in situations where overpressure or vacuum conditions could cause structural failure or hazardous release. So there, unlike the pressure safety valve and rupture disc, we are not letting it go out in the atmosphere or in the flare. Rather, we are trying to store the liquid or fluid in a tank, which is essentially low pressure tank. It will also have its own pressure release valve and rupture disc as well. So these are the safety features of low pressure tanks. So it needs to have a safety valve to vent the excess pressure, the emergency venting and pressure release during fire and external heat exposure. So whatever we have discussed for pressure safety valve and rupture disc, the same thing will come over here. And it also has to have inert gas blanketing and secondary containment. So that is also needed. Inert gas blanketing will reduce the oxygen level to prevent explosion, and secondary containment will have some bund walls or dikes for spill prevention. So these are kind of safety features for low pressure storage tanks. So these are certain conditions that require low pressure storage tanks. So storing volatile liquids at low pressure used for liquids with high vapor pressure such as LPG, ammonia, hydrocarbon, etc. Then protection against the overpressure or vacuum collapse equipped with pressure or vacuum relief valve to maintain tank integrity to prevent implosion during rapid emptying and cooling. Handling large volumes of low pressure gases or liquid that is suitable for atmospheric and slightly pressurized storage of substances like crude oil, ethanol or LNG. Minimizing evaporative losses like it is used in refineries and chemical plants to store petroleum products while reducing emissions. And for preventing boiling liquid expanding vapor explosion, designed to contain vapor safely and avoid sudden rupture in case of fire exposure. So these are certain conditions that require low pressure storage tank. These are few key design inputs that we need to provide for the low pressure storage tank. About the process and operating condition, we have to first mention the stored fluid type, whether it is liquid or gas, is LNG, LPG, hydrocarbon, chemical, what kind of fluid that we are going to store. Then we have to talk about the density and specific gravity because that will affect the tank sizing and structural load. The vapor pressure and boiling point because vapor pressure determines the venting requirement and pressure setting. The boiling point will be important for temperature control and material selection. Although it is said over here, but in Aspen Plus, we do not give such details. We have to just select the stream, and in the stream only all those detailed information will be there, because stream only says that it contains methane or ethane. So what will be the density and specific gravity of that mixture of so much quantity of ethane or methane or all other pseudo components in that proportion? So what is the density of that mixture? What is the specific gravity of that mixture? The vapor pressure, boiling point of that mixture. So all those things will be taken from the Aspen plus property database. Then the temperature condition, the operating temperature and maximum design temperature needs to be specified. Again, operating temperature, if we select the stream, then operating temperature will be taken from there. Then the pressure and vacuum design parameters, we have to specify the design pressure, which should be typically 10 to 25% above the maximum operating pressure. And the operating pressure, it is expected pressure range under normal conditions. Vacuum design pressure, it prevents the tank collapse due to rapid emptying and or condensation. The set pressure for normal venting ensures safe relief of small pressure fluctuations, and safe pressure for emergency venting, that is used for fire exposure scenario. Then we have to mention the tank geometry and structural inputs, that is tank type, whether it will be horizontal or it will be vertical or it will be a spherical tank. Tank diameter and height, it determines the storage volume. Then material of construction like carbon steel, stainless steel or special alloy. The corrosion allowance required if dealing with corrosive fluid, and bottom tank height above grade, because typically it should be 0.5 to 1.5 meter for drainage and maintenance purpose. Then we have to provide the information on venting and relief system design. The relief valve sizing, as per API 2000, we have to ensure adequate venting capacity. So normal venting capacity, emergency venting capacity, breather valve design, inert glass blanketing. So all those things we have to specify. The fluid flow condition, the maximum liquid inflow and outflow, that determines the piping and pump design. Maximum gas flow rate affects the venting calculation. The last but not the least, we have to check the safety and regulatory compliance. Like these are the applicable design standard like API 650, API 620, API 2000, ASME section 8. So whatever you want to choose, you have to. But for various kind of application, their standards will differ. So you have to choose appropriately. And the seismic and wind load consideration, these are required for structural stability. So these are the things that you have to check. Now let us call a storage tank protection. Okay. So here add one. Now you have to enter the design pressure. Okay. So this is the tank one. Now you have to select the stream first. Now this stream, you can leave it empty or you can select an Aspen plus stream. Now if you leave it empty, then many other information that you have to feed in. But if you just select a stream, I mean if you dedicate this storage tank protection for certain stream, then you need not provide those information. I will show you how. For the time being, let us keep the stream empty. Okay. Now for the timing, we give a design pressure. Let us say 0.3 design pressure we provide. Then we have to mention operating pressure. Say vacuum design pressure. vacuum, so it should be negative because it is in gauge, right? Gauge pressure, so it should be negative. Then operating pressure. Operating pressure, let us keep 0.06 bar. Then diameter and height of the tank. Let us take a huge tank of say 10 meter diameter and 10 meter height. Okay. Then maximum operating temperature, let us take 130 degree centigrade. Okay. Now let us go to the normal venting device set pressure. So we go to normal venting. Set pressure, let us take say 80. Now whatever the pressure that we are giving, I am just giving out of my own thought. It need not be the one that is required for the process that you handle. Okay. So if there is any constraint violation in the system, then immediately it will tell in the yellow strip that this value cannot be more than that value, etc. So that you have to check. Now again, vacuum set pressure, let us take -15. Till now I have not encountered any such constraint violation. Now maximum liquid inflow and outflow, let us take 200 each. Okay. And then it is asking for vapor space molecular weight. Now we do not have any information of vapor space molecular weight, right? Because we have not decided about what type of liquid we'll store over there. We have kept this empty. So we have to mention the molecular weight of the fluid that we are going to store over there. So it is asking that information. But the moment we set the stream over there, this information will be taken from there. So if we say take this NGL prod and set stream over there, go back to the normal venting, then it will not ask for such information. Okay. So it will take from there. Similarly, please enter the valid emergency venting device. So go to emergency venting device. Emergency venting device, set pressure 200 millibar G. This is the emergency set pressure. Then bottom 10 above grade M, we have some design value for that. It is typically 0.5 to 1.5 for drainage and maintenance. So let us keep 1 meter, okay? So it is 1 meter, or one constraint it is informing us, that is API 650 is not recommended for a storage tank with design pressure above 2.5 psi-G. Consider switching to API 620. So they are asking us to change it to API 620. So that's what we take and we get OK. So that means we have designed the storage tank, we have designed RD, rupture disk, and we have designed the process safety valve for this particular system, and this design is acceptable. That's what it means. Okay. So that way you can perform the safety analysis of a process after the simulation is over, and you can attach various process safety valve and rupture disk and storage tanks as and where required. With that, we come to the end of this lecture. I hope you have enjoyed it, and we'll come back with yet another interesting lecture very soon. Thank you.